Wednesday, everybody.
Happy.
You're marrying a paper now. Yay.
Okay. You can start.
Yep, the screen works.
Okay, great.
Does the video work, by the way, the stream?
Let me check. Yeah, it's streaming on YouTube.
Okay.
Okay, cool. So feel free to, I want this to be pretty interactive, so feel free to stop if you have any questions. I prepared some slides, but also, yeah, we don't have to get through everything. So, but I wanted to start out just like with a little brain teaser. Just get you in the little math mindset here. So here's a little algebra puzzle. If anyone has any ideas about how to solve it, let me know. Or if you know the answer, go ahead and shout it out. Or
A.
yeah, cool. And how did you see that or figure that out?
I'm just assuming that multiplication is commutative.
Okay. So there's actually a simpler solution here, which is I stuck the answer in the question.
Yeah, but like dA equals AD. Oh wait, yeah.
Yeah. So the question is dA. I stuck the answer in the question, and like I don't know, this is a common thing that we see transformers do. Learn how to copy. But if I told you that there is another way to solve it, if you get rid of the ability to copy, did anyone have a different way to solve it?
Oh yeah, we can see that D equals 1, and then
Yeah, exactly. Yeah, so D is the identity, right? So if you just plug in D is 1, you get out A. Nice. So great, thanks. So this is like a little teaser, but I kind of wanted to analyze, like psychoanalyze a little bit what's going on here. So like when we just see these numbers or letters, like we don't really know anything beforehand about what they mean, but we're able to sort of think about like possible answers without knowing their underlying meaning. And obviously we have some priors as humans and having learned math and stuff beforehand. But it would be a lot easier if we knew, if we were doing math, like simple arithmetic is easier than having to deal with all these variables. And so like if we knew beforehand what the letters meant, like maybe it'd be a lot easier. So this is kind of the idea behind like token embeddings in transformers, right? Like you have some piece of text, like the watermelon rolled off the picnic table, and we tokenize it into some tokens. And these token embeddings, maybe like if you look at the one for watermelon, like maybe these token embeddings encode stuff like this is a piece of fruit, it's primarily red and green, it's like oval shaped, and so this is the nice thing about token embeddings, is that they can encode a lot of meaning as they're trained for a transformer to process text. And like when we go back and look at, like, this has been known since like Word2Vec and even earlier, like if you encode words as like these vectors, like they have this nice, like they start exhibiting nice structure, like nice relational structures. So this is just from the original Word2Vec paper about like this country capital direction, and they have actually a lot of interesting examples here about like associations between words in different contexts. And yeah, like this is maybe the most famous example of taking king to queen, and then they show an example of being able to pluralize, or like in a direction in their embedding space that represents gender. And it's not just like words that have this nice like structure in their token embeddings. A lot of people have been studying like numbers and like the embedding structures that numbers exhibit. So in the original Grokking paper, they studied these different algebra, like different group structures, and trained little toy transformers on these algorithmic data sets on like modular arithmetic. And like, I guess it's hard to get a show of hands on Discord, but like who is like not familiar with like grokking and like modular? I assume most people are familiar. So maybe I'll kind of breeze past these. If you're not familiar, feel free to speak up if you have questions. So just a reminder of like how mod arithmetic works. For example, like if you're like on mod 12, like on a clock, like if you have 9 and you add 4, you like round back down to whatever's past the mod you're at. So 9 plus 4 would go back to 1, right? And when people were like analyzing these small models trained on like arithmetic tasks, they find these like nice generalizing cyclic structures that help like explain like what's getting grokked. So, and then like, for example, like Neil Nanda's paper about studying grokking, I just want to point out, like, he finds basically the same thing. Like there's all these like cyclic Fourier structures happening in these token embeddings, but the thing is that these are happening in the token embeddings themselves, right? Same thing. So there's another paper, the clock and the pizza. Like even though there's 2 different algorithms to solve it, solve these like grokking style modular arithmetic tasks, the first step is always to embed tokens in some nice cyclic structure, or Fourier embeddings, right? And then if you like try and make stuff slightly more complicated, you can even get these like circles of circles style embeddings, which these are kind of nice results, but like sort of a generalization of this idea of like what kinds of embeddings do we see in these number models, and maybe even a more recent paper studying kind of this implicit chain of thought versus supervised fine-tuning on like math problems. They show that the implicit chain of thought model, the one that does well, has this implicit cyclic or Fourier embedding structure of its numbers. All right, so transformers sort of developed this idea that like numbers should have some pre-encoded meaning in them to be able to solve these like arithmetic tasks. And like one question you might think about when looking at all these like toy tasks is like, should I care about these? You know, like these aren't big LLMs. But it turns out like the same periodic embeddings show up in like pre-trained language models when they're trained on natural text, which I think is kind of crazy. And there's been like a series of papers that are like converging on this idea, right? So, for example, here's just a couple examples. So like Hu et al. And Kantanemi et al. Kind of show these nice periodic structures of token embeddings. Similar thing, like models sort of learn these like periodic heuristics for working with numbers, or even like for GPT-2, they show these like modular patterns when they do Fourier analysis on them. This is also an interesting paper, I thought, that is semi-related to this. So if you like freeze a transformer and only train the embeddings and unembeddings, you can sort of analyze the kinds of tasks that a transformer like this might be able to solve. And it turns out that when you train it on like modular arithmetic tasks, it also seems to learn these like periodic structures just in the embeddings. So like the embeddings are actually a very powerful tool for solving at least these algorithmic style tasks. Like you don't even need very complicated weights. You can just pick randomly initialized weights and just train the embeddings, and you're able to solve this kind of thing. Yeah, any questions up to this point?
So when you say that they are these patterns are found in pre-trained language models, I saw that you in the example that you mentioned, there's like Llama 3 8B and GPT-2 XL, right?
Mm-hmm.
So What's the most capable like model that you've seen these in? That
I
we've
guess
run
like
experiments.
yeah, I guess open weight model is probably like one of the llama 8B. Like Anthropic, I don't know if you've seen like Wes Gurney's recent paper on like predicting new lines, where they sort of show that I think it's like a version of Claude, maybe like Claude
I think
Haiku
it's haiku if
2.5
you mean
maybe.
I think it's haiku.
the
Yeah.
counting task. Yeah.
Yeah, so like I mean even like
Geometric
Claude
quantity.
Haiku has these style of like periodic numeric structures. Yeah. But as far as like open weight models, my guess is probably the biggest one somebody's looked at is like one of the llama, like llama 8B or something. I don't know if I haven't seen any bigger
Okay.
ones, but
I
my
think
guess is this is pretty universal.
Yeah, I think also like on the on one, I think maybe on the one. No, I know if it was also haiku or it was a bigger cloth, but I think there is another Anthropic paper like of the one where they did was they were doing using sparse transcoders and using doing the attribution graphs. And in that one, they didn't find something like this, but the attribution graph that does addition there looks a lot like if what they show on the Western paper, what it looks like when you are taking, linear, when you are taking discrete slices of a this kind of structure, and it looks like it's doing a bunch of weird stuff with modulus, but that's just if you would do a line on a circle, it's going to do something that has the same value modulo something, because it's when it turns into in the circle. So I think there's at least evidence that in bigger models this is also happening.
Yeah, so I guess I'm providing this just as background. Like my guess is there's been some like theoretical work, for example, showing that like these Fourier embeddings are like the max margin solution for like encoding numbers. So like I think it's nice that transformers are finding these, and even like big transformers are finding these, but it's sort of just background on like why background for like the setting that we're studying in our paper, like why this might be like is something
And is
interesting
this
to
the
think about.
primary method for representing numbers, or are there like multiple redundant representations, like based on the task, which and decides a different representation to use based on what might be optimal for it?
Yeah, so I don't have a solid answer. Like, it seems like there's this paper that talks about like how models do arithmetic with a bag of algorithms. So like some bag of heuristics where like there's stuff that checks like, oh, like this number is like, 5 or in between 5 and 25 mod 50 or something, So I don't know that it's like the only way that numbers are like encoded, but it is at least one way that models seem to be like transformers seem to be working with numbers is sort of these like Fourier structures.
Mhm.
Yeah.
Yeah, but I
So
think I wanted to. I think that it's not obvious that the modulo that paper that's not also a Fourier structure, because I feel like with their methods, if there was a Fourier structures, you will probably get something like that. But yeah,
So right, like it's not exactly the same, but it's like I guess in my head they're similar that these are like uh cyclic in a sense, right? But yeah, so it's not the main point of it's sort of just some background. Um so reminder, just like from the initial thing we were talking about, like these transformers seem to encode these like Fourier or cyclic like structures in their token embeddings, and they all seem to rely on this idea that like tokens have fixed meanings. Like the number 2 always means 2, you know. And then like based on where it appears in the context, maybe you have to build it up into the number like 253 or whatever, but like 2 has its own meaning, right? And But like sometimes we want the context to change the meaning of a word, right? So sort of like in natural language, like tokens don't always have fixed meanings, right? So here's just 2 example sentences, right? Like, so the feather was so light it floated in the breeze, and please turn on the light so I can read. You know, like here, the word light, we want the context to be able to modify the meaning of the word. And so like this is sort of in conflict with this idea that like, oh, like we should just like pre-encode the meaning of words in the token embedding, you know. And I think this is like one of the beauties of transformers, right? Is they have both these pre-encoded meaning, but also like the ability to learn from context. So for example, there's this paper you may have seen called GSM Symbolic that sort of takes a well-known math benchmark called GSM AK, and they sort of parameterize it with some variables that allow them to sort of test this idea of whether language models can like reason abstractly when you just modify the value of a variable. So instead of having like specific names, you can just like take some template of the same problem and like cycle through a bunch of values for the same variable, and then test like the limitations or the abilities of transformers to reason like this. So I think this idea about like variables is actually really interesting, because that's sort of what we want. Is we want transformers that can reason about symbols whose meaning can change, and they do this through in-context learning. So I'll just review some things about in-context learning. So our work is sort of at the intersection between sort of like these like arithmetic study and like studying transformers doing in-context learning. So for those who aren't familiar, like in-context learning was sort of coined in the GPT-3 paper, where they show that like language models are able to generalize behaviors just from a few examples shown in the context. And it was pretty surprising at the time because like traditional learning was sort of thought of as like, well, that's what happens during training, but ICL is happening like at inference time, right? Yeah, and there's sort of we'll skip this, but like there's lots of different ways that people have tried to study sort of in-context learning. So here's like an example of like sentiment analysis where you give some sentence and ask it whether to classify whether it's positive or negative. That's the traditional task. And then this paper, this large language models do in-context learning differently, shows that like large models are able to sort of map these abstractions of like positive and negative sentences to randomly chosen semantically unrelated words in the context better than small language models can. So they sort of are using this to imply that big models are able to abstract better than small models. And in the previous work of mine, we sort of showed that like one way that, or like one reason people are using in-context learning is sort of to like induce these like behaviors or functions from that we like show some demonstrations of a behavior we want in context, and that you can sort of pick out these functions from the activations and induce them in other settings. But when we are studying these are all sort of things that might be able to that like sort of rely on meaning that's encoded in the meaning of the words themselves. And there's maybe a more recent paper studying kind of how in-context learning might be able to like update the meaning of token embeddings as the length of a context grows. So in this work, they sample like words on a grid. They have some fixed grid and then sample random walks on a grid, and show that as the context length grows, the grid pattern sort of emerges as you do like PCA on the representations of the tokens, which is kind of interesting, right? So this is sort of an example of the model being able to overcome whatever priors that the original token embeddings have in favor of something that it's trying to model in context.
And for people who are interested in like digging deeper into this, I think Agdeep gave a talk about this at Stanford, which is on YouTube, right? Where he goes.
Yeah, Akdeep's done a lot of good work related to this. I definitely recommend checking it out. There's been some nice follow-ups as well to sort of this idea. So in our work, we're sort of studying transformers' ability to reason in context, but without, we sort of wanted to disentangle the ability to reason in context with the model's sort of tendency to encode meaningful information in the token embeddings. Sort of trying to get over this problem of like, well, do I have some priors baked into the tokens that I care about? And so what we do is we develop this task that we call in-context algebra, so that we can study like what computational strategies that transformers learn when the tokens don't have any prior meaning, that everything that they have to learn is sort of inferred from the context. So the thing that we do is this is like a high level overview of where we're going to go. So we train transformers to sort of simulate a mixture of finite groups, and the tokens are variables. All the tokens are variables, so that their meaning can change between every sequence, and the model has to sort of infer what the tokens mean just based on their interactions with other tokens in the context. So here's just like an overview of the rest of the presentation. Yeah, so I'll give some background on like so basic things you should know about groups and just like algebra to sort of get the gist of what's going on, and then we'll talk about like the task and then like our training setup and like sort of what these transformers learn, what kind of strategies these models learn to reason in context. But yeah, so any questions up to now?
Nothing from me, but there might be something in the chat.
Oh, I didn't realize there was a chat. Let me just see. Okay.
I just checked it. There's nothing in the chat.
Okay.
Yeah,
I have
great.
a question.
Yeah.
Regarding the graph structure that you showed, that people came up with by applying the PCA. How do we know? Yeah. How do we know that there is indeed a causal connection, or like you showed certain edges between those points in the PCA graph, but how do we know that there is actually an edge between those clusters? Or
yeah, so I think in their paper they do have some experiments where they try and steer the model to like a different point on the graph based on so like given like let's say you're at I don't know a plane or something, they try and use these learned like centroids to steer the model to say something else. And I think there's like I don't know if it's like perfect. I don't think it's perfect, but I think there is some like some evidence at least that they're somewhat causal. Yeah.
One issue is that every time you do PCA, you have to redraw the axis vectors. So in these screenshots, it might look like the graph is rotating. Like you can see that the blue point seems to be shifting, but it might not actually be rotating. It's just that PCA is like not the like axes are not aligned in all of these graphs. So it could be learning like the same space, but it's just like rotated differently. It just looks like it's rotated differently because it's not the same axis vectors every time you redo PCA.
Okay, and even more so, I think it might not be necessary that the PCAs are the same. Is that also true? Like when you keep changing the context length and you keep building the graph again, like or plotting the graph again, then the PCAs might be different. Maybe I'm wrong.
No, I think that's right. Yeah.
Okay. Yeah. Thanks for answering the question.
Yeah. Cool. So let's
There's a
jump
question
in.
in the chat.
Oh yeah, sorry. I let me see if I can see. I don't know where to see the chat.
If on the left, if you hover over the reading loop, you can see
Show chat.
open
Here
chat.
we go. Okay, great.
Yes.
ICL doesn't update embedding weights. I don't understand the slide which says ICL updates embedding tokens. Okay, good question. Yes. So let me. So you're talking about this slide, I think, right? So yeah, so that I put updates in quotes, right? So the embedding weight, the token embedding weights are frozen, and they have some information stored in them. But I guess what I was trying to get at here is like, this paper shows evidence, kind of the idea that the information that's encoded in or like the priors that are encoded in token embeddings can sort of be updated or overwritten with information that's maybe more salient that's in the context. So instead of like apple meaning like a fruit that's red as like its primary axis, in this context, it's like more associated with the words bird and house, for example, than it is for like a mango, which like is also a fruit. So like just naively, I would expect, for example, like mango and apple to be more similar in like token embedding space than apple and house. But as the context length grows, it sort of updates its representation of that word over time, if that makes sense. That's sort of how I
mean
view
like
what this work's trying to say. Yeah.
you mean later in the model?
Right. Yeah. So this is also like midway or close to the end of the model's processing. Yeah. Yeah, sorry about that. Sorry that wasn't clear.
I had
Thanks
this
for the question.
confusion as well and answered it.
I think this was in layer 9 of like Llama 2 8B or 7B. Yeah.
Yeah, I don't remember the exact layer, but that's kind of the idea of, and so like I guess there's like maybe a recent follow-up paper that maybe has clearer evidence of this. So I don't know if you guys saw, there's a paper that sort of takes the idea of jailbreaking. Like I don't remember what it's called, but basically they take a bunch of prompts about bombs and then they replace the word bomb with carrot. And then generate a bunch of sentences about carrots acting as bombs, and then like ask the model like, tell me how to build a carrot, you know? And the model like is happy to comply with telling you how to build a carrot, except for it's like jailbroken and gives you instructions for something for like building a bomb, but as a carrot. And so in that paper, basically they show that like the model has updated its meaning of the word carrot to like to know that it is like means bomb. Yeah, I don't know if is that like paper familiar to you guys? I don't know if maybe I'm just rambling.
I don't
But it's
remember the exact paper, but I have observed this property in like my own like LLM chats. Yeah, that this model indeed has this capability. I'm not like I don't know what mechanism it might be using in order to like do that meaning change.
Yeah, so I'm not exactly sure either, but I guess in my head, yeah, so I know I could go find the paper, but
No, that feels like so if I understand it correctly, the other the example you have on the screen, right? It's more when you see talk about the representation of the work, you are talking about the same token position but on a later layer, right? And the other and that thing is like it doesn't have to necessarily be the same as the meaning of the word carrot or something, because the model can be moving the information around and be, using the word carrot somewhere else.
Sure.
And feels like the mechanism. There's a mechanism for doing that with carrot. It doesn't have to be the position that corresponded to the carrot has something else now.
Right. But I guess like if you were to ask about the word carrot in that context, so I pasted the paper in here. They call it in context representation hijacking. But if you were to ask about the word carrot, it seems like the model treats carrot like as a bomb, basically.
Yeah.
But you're right that like it doesn't have to be at that specific token position. Yeah. But anyway, so all this to say, like, there's evidence that like the context can sort of like influence how models think about specific tokens that overwrites priors that are baked into the token embeddings. That's all I was trying to get at. Yeah, so let's move on here. So okay, so yeah, how many people are like familiar with like groups and stuff like that?
Familiar
I think that the
enough.
question is who isn't familiar.
Who
Sorry.
isn't? Yeah. How much time should we spend on this before we dive into the meat of the paper versus like
I'm not
is it
familiar.
worth-
Or like
Okay,
I know
great.
they are a thing. I'm vaguely, but not.
Okay. That's fine. I think maybe it's a helpful refresher as well for those who maybe it's a little rusty. So in our paper, I guess it's not like critical, but it is like somewhat helpful if you understand kind of what's going on here. So we use groups to sort of study this idea of what do transformers learn when the tokens are variables. So a group is just a set that has an operation, a binary operation. So it takes in two values and outputs a third value. And the operation has three, so the group has three properties. So the operations are associative. So if you put a parenthesis around like A times B, then times C, it's the same as A and then parentheses B times C. And then every group has an identity element, which like in the first example that we saw at the beginning of the presentation, is like for multiplicative things, it's like the number 1, right? So like A times E. So if E is the identity, A times E should be E or A, and E times A should be A. And then in every set also has an inverse. So there's some way to get back to the identity element. So A times B is E and B times A, if those are the inverses of each other. So we look at two main types of groups. So the first kind of group is are called cyclic groups, and this is similar to like modular arithmetic. So for example, like if you have a cyclic group with 8 elements, you might see something like this, like 3 plus 2 is 5 mod 8. But if you had only a group with 4 elements, like 3 plus 2 would be 1 mod 4, right? Similar idea. And then we also study a different kind of group that are called dihedral groups. And these are just like the symmetries of an n-gon, like a polygon. So, and there's two kinds of elements. So in cyclic groups, there's only one kind of element. It's like you can only do like rotations around a circle, basically. But for dihedral groups, you have rotations and you also have reflections. So I think this is a nice little example of kind of to see what's going on. So let's imagine you have like the letter F in the middle here, a big F. And so the identity, which is this E, I don't know if you can see my cursor, but so the E here, like the identity leaves the F unchanged. And then they have what they call here, so these are different elements of a group. So here, this is, so we call this D4. So there's 8 elements in D4, which are just all of the symmetries of a square. And so like these are, so the A's are rotations of F. So like A, you just like rotate this 90 degrees to the right. If you apply A again, it's like rotating it 180 degrees. If you apply A again, it's like a 270-degree rotation. And if you were to apply A 4 times, you'd get back to the identity, which is just F again. And then they also have ways to represent these flips or these reflections. So like reflection across sort of this y-axis, they call B. And then you can compose these rotations with the reflections to get other orientations of F. So I don't know if maybe that's like helpful to sort of see like how would you get out the elements of this group. Yeah, we'll skip that. Oh, sorry. So any questions about like dihedral groups or?
So reflection along the x-axis would be a different reflection. Like would be a different operation from reflection along the like y-axis, but you don't need that operation here because you can kind of recover the same states.
Yeah, exactly. So like if you were to imagine like a square, like reflection across the x-axis would be like over like across A, you know. So in our F, for example, it would be this one here, the third on the bottom. So you could represent that as like its own letter if you wanted, but they just use shoot, I forget what the name of it is called. They're called generators. So there's two generators for a dihedral group, and they are like the primary, they're like kind of like basis vectors, right? So like to reach all of the elements in a, like to reach all the vectors in a vector space, you have like some number of basis vectors. For groups, they're called generators. So like for groups, you would just need like rotation, like one rotation and one reflection for dihedral groups. And so like you could call this something else, but they're showing it just in terms of like what sort of composition of generators would you need to get to this orientation, basically. Does that answer your question?
Yeah.
Cool. Okay. Great. So yeah. Oh yeah. So if a group is like, one thing people say is like if a group is abelian, that just means that the operation is commutative. So A times B is the same as B times A. So this is true for cyclic groups, like that is always true. But then for dihedral groups, not every pair is commutative. So most dihedral groups are not abelian. And then the order of a group is just like the number of elements in the group. And then there's all sorts of other like algebraic structures that exist. And we sort of test on some of them to sort of show, like test the limits of the transformers that we train to see like what kinds of stuff are they actually learning. But mainly we focus on groups. Okay. So yeah, so any questions up to here? Otherwise, yeah. And I don't know, is there like a time? I'm trying to time. What's what I have about? Is there a time limit? Should I end in
Not
13
really.
minutes?
I mean, sometimes we go very far. It's mostly when you.
4 hours. Yeah, the time limit is 4 hours.
We have been for 4 hours, but usually people start leaving before them. But yeah, don't worry if to be on time.
Okay, let me just check the chat real fast if there's anything else. Okay, I think we're good. Okay.
Yeah, there's just one thing. I'm not sure. Do you know the toy model of universality by Neil Nanda?
Yes. Yeah. Bilal's paper. Yeah.
Okay. Yeah. You maybe, or maybe that's for later discussion, since how it relates to this paper. But maybe that's for later.
Okay. Yeah, we can chat later. Cool. So this is swapped out some of my slides. Sorry that this doesn't have a little caption, but this is like, how do we generate one of the sequences for our in-context algebra problem? Let me see if there's a better. Yeah.
You ended your stream.
Oh, sorry. Okay. Let me see if I can get back here. Share
Also, you might
screen.
will fix it on YouTube, Victor.
Sorry about that.
Are you online, Victor?
Oh,
do
yeah,
you hear
don't
me,
worry, it's
Victor?
still working.
Okay. Okay, good.
Okay, so
Since okay,
now I need to do this again. View, present your view, and then you guys should see.
yeah, good. Works, and we can see.
You can see this. Okay, so the way that we construct algebraic groups is we sample some set of groups. So like here, maybe we sample.
We see Discord now. So
Okay,
maybe,
let me. Sorry. Change the stream. Oh, why doesn't it show up? Oops. Boy. Okay, 1 second.
Also, Victor, you should in this stream turn off sound of the stream because there's double sound when someone is talking.
Okay, I didn't.
After the stream goes online again, you wanna share your whole screen and show some drawing board. I think that's what you're trying to do.
No, I'm just trying to reshare, but for some reason
Okay.
I don't see my presentation anymore.
You
Let
just
me
close it.
Okay,
Let me just close
maybe.
it.
Okay. Yeah, either restarting Discord or restarting the app should, if suddenly it's not in the that you cannot pick the application.
Yeah, let me see.
Or you can share the whole screen. That's also an option, I think.
Okay, let's try again. Okay, I'm gonna restart Discord because I don't know. It's not showing up.
Okay.
Be right back.
Oh, yeah, maybe just rejoining as well. But yeah, this is better probably.
It's okay. We have time. Well, maybe some
Yeah.
people will have to leave, but yeah, we've been for 4 hours on time, so
Yes.
it's
Okay.
okay. We have time. There have been some days where we've been for 4 hours, so
Okay.
5 as well.
You guys can see that now.
Yes,
Okay.
we can.
Great. Okay, so yeah, right. So we have this like in context algebra task, and the way that we generate all these sequences where these tokens are variables in the following way. So we sample some set of groups. So in this case, we've got 3 groups. So C3, C5, and C4. And they have 3, 5, and 4 elements respectively. And then we assign like elements to each of these, or we assign variables to each of the elements in the group. So for example, like C3, the identity in C3 gets the letter J. The first element in C3 gets D, and the second element gets E, and so on, right? And then to generate a sequence, what we do is we sample facts from some group. So like, for example, in C4, like 1 times 2 gets us to 3, and the corresponding like variable version of that is P times N gives us I. And so we just do that for a bunch of different facts. to get some sequence where at the end we're trying to predict some unseen interaction between elements in a group. I feel like there's some contextual slides missing here. I'm sorry, my slides sort of got put out of order. But does this make sense? I don't know if there's questions about that. Okay, maybe
Makes
the
sense.
slides will show up later. Yeah. Oh, sorry. Go ahead.
I just thought makes sense.
Great. So, okay. So, right, and this is just a different view of thinking about. So, like, if you were to represent all the facts of some group in like a table, we have some mapping between the facts here and the facts in like in variable form, right? Yeah, and so for for every sequence, there is a different mapping, and there's different groups that are sampled, and so there's many orders of magnitude different kinds of sequences we can sample via this sampling process. Right. So what we do is, given this like in context algebra task, we train our own transformers from scratch. And the main one that we'll analyze here is just a 4-layer transformer. It's got 8 attention heads per layer. And then the vocab, there's just like 16 of these variable tokens. And then there's 2 special tokens, which are like the equal sign and a comma as a separator. And then we just train using autoregressive loss at every token. Yeah, so the first thing I'll show is just like, can transformers like learn this kind of task where like all the tokens are variables? And yeah, it turns out that they can. So this is showing just model performance as a like a factor of the number of facts that are shown in context versus accuracy in predicting some unseen fact that didn't show up in the context, and then split across different groups. So these are the cyclic groups that we talked about, and then dihedral groups. And then we also test on some other kinds of groups that we didn't use during training, as well as some like non-group structures. So these are the first 3, so C4 cross C2, and then C2 cross C2 cross C2, and Q8. So these are like different order 8 groups that were unseen during training, and turns out like even though like the model can still learn those pretty well. And then these other 3, a semigroup, quasi-group, and magma, are like some non-group structures. And like I think it's kind of interesting that like the model is able to like perform on the semigroup pretty well comparably to these other held out groups. Whereas like for quasi groups and like magmas, the performance is like pretty abysmal. And so this like sort of like can give us some intuition as to like the kinds of things that this model is learning is like probably heavily relies on stuff that's like specific to groups, and I'll show later like maybe why quasi group is like slightly better than. So magma is basically, there's like no structure in a magma. The only thing is that like the operation has to be closed, so that you can't just like, and that's basically it, right? Yeah, question.
Yeah. So for the first graph, I noticed that C3 probably that's also having a lower accuracy. And is there a specific reason for that?
Yeah, so C3 only has 3 elements, and so like the total number of facts in its table, there's like 9 facts total. And so if you like have a super long sequence, like 200 facts, there's just like a lot of repetitions of the same fact over and over and over again. And for some reason that hurts performance. I don't have a solid explanation beyond that, but yeah. And you can kind of see a similar thing like for the for the medium-ish size groups like C4 and C5 also like drop a little bit as the context goes up.
Yeah, makes sense. Okay.
But yeah, C3 is
So-
definitely like an outlier there. Yeah.
Can you specify again what exactly is in the training data and what exactly is being put into context? That's not in the training data.
Yeah.
So-
So the training data is so we sample data like this. So you can sample groups, and the groups you can sample from are the cyclic and the dihedral groups. But the mappings, like the between variables, changes for every sequence. So these two are like in distribution, I guess. And these are very out of distribution. But then these are also showing like held out performance. So when we train it, we don't necessarily like it's possible that this particular like question could have shown up in the context before. But when we test, we make sure to that these are like held out within the context as well, so that it can't just like copy the answer. So it has to learn stuff beyond just like induction, basically. Does that answer your question?
Thanks. Yeah.
Cool. So, right. So based on like looking at the performance of this model, and sort of the exercise that we did at the beginning of like trying to hypothesize like, oh, well, how would you solve one of these like algebra problems where you don't really know what the meaning of the variables are, but you can sort of infer from their interactions like what they might be doing. We came up with like 5 different algorithms that can solve sort of these sequences with different conditions based on like what's in the prompt. And so we made like 5 data sets that try to measure kind of the coverage of like how much of the data set could we actually solve. Because I wasn't sure that like how much of the task is like actually solvable. So here are like the 5 data sets. So that's a lot of text, but I'll just sort of walk you through what these are. So like verbatim copying, this is like standard induction. So like the sequence, so the question like AB showed up in the context before, and you're just copying it again. So like, does the model learn how to copy or not? The next thing we test for is like, does the model learn like this sort of heuristic of commutativity? So like in many groups, like cyclic groups, like if you know AB is C, then like a lot of the time, like for cyclic groups, it definitely is true that BA is C, but like we also train on dihedral groups, so this isn't always true. And so we sort of test for whether models like learn this commutative heuristic. And then we also test for these other things, which are like, does the model learn about the identity rule? Does it learn about like associativity? So these are like properties of groups. And then the last one that we test for is this thing called closure-based cancellation, where the model sort of tracks both like which elements in a sequence are related to each other, and then which ones can we eliminate based on like the cancellation law. So it's sort of like Sudoku style answering. And I can, if I haven't, let me see if I can.
So is it like elimination kind of a thing? Like
Yeah. So it's a combination. I guess it's like it is elimination, but it also is like constrained because so if we go back to here, like the sequences that we sample don't just contain one group. And so like the other thing that you have to do is, I guess as maybe part of your elimination process, is like determine which elements go together in the same group.
Okay.
Right. So like E and J never interact with K and A and B because they're not
Oh,
in the same group.
when you generate the mapping from the group elements to the tokens, is there a case where there's like reuse tokens? So like C3 could use E and C5 could also use E, for example, for a different element, or that's not the case?
No, yeah, we make sure that they're always distinct and never repeated.
Okay.
Also, I noticed that we are not checking for inverse elements, I guess. The inverse operation.
Yeah. So the inverse is sort of implicit in this cancellation rule. So what I guess we could pull out the paper, but there's a little note about like the cancellation law. So let me see if it's let me just go grab a if I escape, is it gonna kill the thing again?
If it's tedious, then no worries. I can check the paper once.
So basically the like the assumption about inverses is sort of implicit in this idea about cancellation. So like let's say we have a fact like so here's an example. So like let's say in the context we have a fact that says xb equals g, and then our query is something like xy equals. Since y isn't the same as b, what the cancellation law tells us is that like xy can't be g. And the way that you would like prove this is like by applying inverses. Like that's what the cancellation law says. Yeah.
Got it.
Yeah, but I guess the intuition here is like I'm sure most of you have like played Sudoku. So like basically you can like pick out all of the things that share X or Y. Like if your query is X or Y, you just like go back in the context and look at all the things that share X or Y, and you can like eliminate answers like this that don't share that share something on the left or something on the right. And we'll dive into and so like if we so what we do is we construct like small data distributions that like explicitly have these properties, and then test the model for whether it can solve those kinds of sequences or not. And so for like 4 of the 5 mechanisms that we hypothesize, it seems like the model has a pretty good rate of solving them. So like it knows how to copy. It learns this like commutative heuristic. It's very good at solving the identity. It's actually kind of bad at solving these like associative problems. And then it's like pretty good at solving these cancellation problems. And so in the rest of the paper, what we do is we sort of analyze like how the rest of how these 4 mechanisms are like implemented by the model. But first I'll show sort of like the coverage of like of the overall data distribution that these algorithms cover. So on the left is like the training distribution, where copying is allowed. And so if you just like we like code up what these algorithms are able to solve, and find that like basically this is like around, I don't know, 60% of the AUC of the training data can be solved just by copying. And like as the sequence length gets longer, like you can just copy. So and then the purple shows like what of the ones left over can you solve via like using the commutative law, and then like applying the identity rule, applying cancellation, association, etc. And then in black we have like the empirical model performance. So one thing that I thought was interesting is like we came up with these 5 heuristics, but the model still has like better empirical performance than what we were able to explain just from these 5 simple algorithms. even though like these 5 can explain maybe like 90% of the data distribution, the model learned something else that we didn't quite pin down. So still an open question as to like we haven't fully explained this model, though like I think we do understand a lot of what's going on. And on the right is the same kind of thing, same kind of analysis, but on the test distribution where copying isn't possible anymore. And so like around 30% of the cases can be solved with the identity algorithm. And then on top of that, you can get up close to like, I guess the AUC here is around like 30-ish% can be solved via this like Sudoku style cancellation law, which like gets better as you increase the context length because there's more things that you can cancel. And then like like applying the associative law can solve a good chunk more. Which like here there's even a larger gap, and because the model doesn't learn associativity, there's maybe even more things that the model has learned that we couldn't quite pin down yet. So there's definitely some room for analyzing this setting more, but now I'll just talk about kind of the things that we were able to understand from what this model learned. Yeah, but maybe happy to stop for questions here.
One question I probably would have missed maybe when you started discussing the paper, but why only groups? Why not some other structure? Like, I mean, we're studying algebraic equations, whether they can be whether they can be generated, right? But why only groups?
Yeah. So it's a good question. I think we stuck with groups because like it was maybe the most similar to stuff people had done in prior work.
Yeah.
But like it doesn't necessarily like, and the models that we analyzed, we trained on groups, but like I guess like theoretically our setup doesn't have to be groups. Like you could have the variables represent things in non-group structures and train it on that and see what it learns. That might be interesting. Though like, yeah, I mean, I think that definitely could be done, and I think it'd be interesting to see what happens. Like maybe it learns different heuristics for for other structures than you learn when you just train on groups. Yeah.
Makes sense. Is it the case? Sorry, I'm not very well versed in high level math, but is it the case that the cyclic groups will always be groups? I mean, I guess by definition it would be maybe a very naive question, but that would make sense if we see any periodic structures. Then it's probably better to start with groups rather than starting with other kind of yeah. I guess
Yeah,
I understand why the motivation now better.
Yeah, so I think I mean, so like there's been a lot of work studying like modular arithmetic, which can be like reformulated as these cyclic groups. So that's maybe one of the main reasons for choosing to keep that. But we also wanted to we added dihedral groups because we didn't want to just everything be so uniform. Like wanted some different structure, I guess. But yeah, there's all kinds of other groups beyond like cyclic and dihedral groups that it might be interesting to study what sorts of algorithms get learned. Yeah.
Yeah, good. Thank you.
I have an additional question if we have time.
Yeah.
The groups you've done so far are fairly small, like 12 elements within the groups so far.
Yeah.
Have you done any experiments with larger groups or potentially groups where it needs multiple tokens to represent an element? Because I feel like models might begin to struggle there to kind of generalize the concepts that it's learned.
Yeah. Interesting. So I guess there's two questions here. So we did play around with training on larger groups. You can do it. You just need a bigger model. But I guess we wanted to like keep it contained and didn't really explore that. Like we had some preliminary, I guess, investigations on like the size of a group, but figured the task we set up was like complex enough with like all of this mixing of groups that if we had really large groups, you need, so like if you have really big groups, you need even longer contexts to like be able to show elements of a group interacting with each other. And so that was one of the constraints, I guess, was like context size as well.
Gotcha.
But yeah, and then in terms of like representing elements with multiple tokens, we didn't try that, but it might be interesting. Like I could see a natural thing being like using the generators of a group somehow to like represent the elements of a group or something. Yeah, I don't know. It'd be interesting.
All right. I was just curious if you guys poked at that at all.
Yeah, we did not. It'd be cool to see because like I know there's like this this work on like detokenization, you know, where like if a word that like a normal word like just gets like tokenized weirdly, like language models sort of have this ability to like understand what that is, you know. And so like I wonder if these models would like have some similar like detokenization process or something if you try and represent them with multiple tokens, you know.
Yeah.
Yeah, but I think that'd be interesting. But no, we didn't do it. So.
All right. Thank you. I was just here. Not in your paper, but you know, there's a lot that doesn't go in, so I was wondering.
Yeah, fair. Yeah. And yeah. And yeah, if anyone, I mean, happy to feel free to DM too if you have other questions or like things you're interested in following up on. Like there probably are a lot of things that are not in the paper that we tried or whatever. So yeah. Cool. So
we should train on monster groups.
I'm not familiar with monster groups. Is that
the monster group is like some 200,000 dimensional group. It's like the biggest. I think it's the biggest group or something. It's part of sporadic groups. Yeah, group theory is fun.
Yeah, so I'll preface. I guess I'm not a group theory expert, but I did spend some time learning some stuff for this paper. So yeah, if there's more mathy people that have more insights, would be happy to hear. Okay, let's see. So yeah, so maybe copying isn't that interesting. We're kind of running a little bit low on time. But so like I guess the first mechanism we look at in the paper is like copying, which is like very much induction style copying. If you're familiar with like induction heads, this probably isn't too interesting of a result, but we find that like models learn the same kind of like copying here in this setting, which makes sense. It's a pretty simple strategy, and that there's just like one head that like has this copying behavior. We also see like this, like it turns out that the same head that does copying also has this like commutative behavior as well, which I thought was kind of interesting. So if you take these copying sentences and you remove the exact copy from the sentence, it turns out that they'll go ahead and attend to the commutative copy instead and promote that token. So that was kind of cool. And then like I guess we see these other behaviors where like when there's no instance of a repeat or a commutative pair in the context, then like this one head that we found that does copying just like does nothing. or yeah, just attends to itself basically. And then sort of to test that like this head is doing copying, you can sort of inject these like fake facts that aren't necessarily true. So like we could stick like KC equals J in there instead of F and show that like, oh, it just basically is promoting whatever kinds of tokens it attends to. Yeah, so I'll breeze past these because I think the copying results are maybe less interesting than the other two mechanisms that we found. But happy to answer your questions if there are any. So the second mechanism that we found is kind of this identity element recognition, which is one that pointed out at the beginning when we were talking about like how might we solve this algebra problem. And so the identity is basically the only thing. So we did a lot of like PCA experiments trying to. So one of the hypotheses we had was like, oh, maybe when we train this model, what it will do is learn to like reverse engineer what these variables mean, like what group elements these variables are assigned to, and then just like apply the same style of like grokking out like clock or pizza algorithms that we had seen in prior work. Like that would be a potential solution, is just learn the underlying mapping and then apply it, and like you'd solve it easily. But it turns out we didn't like see any nice cyclic structures in the embeddings at all. And the only thing that we could really find when we were doing like studying and analyzing the either the token embeddings or like the representations of the model is like in the layer 3 in the final layer attention module, we find this like nice separation between like identity facts and facts that don't end in an identity, and which I thought was kind of interesting. And so like if we take this direction from like identity to not identity, we find that it actually represents like promoting symbols that are in the query, in the question. So let's say we have like some sequence like this, and the question is like A times E. So normally, like if and then we had some fact in the context that showed like E is an identity. So like E times F is F. Here, what the answer should be is A, and the way that the model does this is it has a head that promotes both of the answers in the question, and then it also has a head that demotes the identity element. And so like via a combination of these, you would get out the non-identity element, which is exactly what you'd want. So I thought this was a pretty clever mechanism.
Can you explain the query promotion again?
Yeah. So like at this equals token, there's one head that promotes both of the answers in the question. So like in this case, it's A and E.
Oh, I see now. Yes.
Yeah. And what we do is like to verify that like this like direction in the so this is, we just like do PCA on a bunch of attention outputs and like see this nice pattern. But to like test whether this like direction is like represented, like is like causal, we sort of like try steering with this direction to see what happens. And so if we have some sequence that is not an identity question, so like D times F is the question, and neither of those are an identity fact or an identity element. What we do is if we steer towards the identity fact, so if we take some red fact and we steer towards the blue fact by like adding this direction during inference, what we get is something like this, where where before the model would have said like E with pretty high confidence, these are like logits. Now if we add this like direction, the model says like D and F with like almost equal logits. So what we take from that is like this direction is basically managing whether the model decides to promote the questions or like the symbols that are in the question or not. And then you can get like better steering if you like add a faked identity fact or not. So if like you can take a question that's not an identity fact at all, steer it towards the bias of like you should promote the answers in your question, and then you can add a faked fact that says like, oh, you know what, D is the identity, or you can add a fact that says F is the identity, and then this like induces this identity demotion mechanism, which then promotes the opposite letter, so like getting out D or F respectively. Let's see, there was a question, Bernie. Yeah, there is a GitHub. You can check out. Here, I'll just put it here. Here's the project page, and there's a link to the GitHub through there. Beginner question here: how's it inferred that certain head promoted the particular behavior? Okay, great question. So, yes, let me answer that. Right. So, the way that we like tell, I guess, the way that we're telling whether a head has some particular behavior is we take the attention head output and then just pass it through the model's unembedding. So this is basically like logit lens. People call this like the logit lens or like direct logit attribution. And this gives you a sense of like what this head's contribution is in terms of logits. So it's like it's not perfect, but but you can also do some other things to sort of test it. So we have these like steering experiments where like if we steer in this direction, we see these values increase, and then like for example, if we like add a fake fact that this isn't a true fact, but it because F isn't normally the identity in this sentence, but if we add a fact and then show that like it decreases the probability of F, then it matches sort of our intuition of what this head is doing. I don't know if that answers your question, but cool. Great. So yes, so let's okay, and then the last mechanism that we look at in the paper is called closure-based cancellation. And so I don't remember who asked about like the implicit assumption about inverses, but this comes from this. Like, so the cancellation law says like if x times y equals x times z, then y is z. And the way that you would get that is like by applying x inverse on the left here, right? And the same thing here, like if yx equals zx, then y equals z. The way you would get that is by applying x inverse on the right. And so we sort of use like the contrapositive of this, which says like if y is not z, then these two these two facts aren't equal to each other. So like xy is not xz and yx is not zx. But the way that we can think about this is there's sort of this high level intuition about like the model sort of builds up some set of plausible answers, which we call the closure, and then things that it can eliminate, which we call like the cancellation or elimination set. And then like computing sort of the difference of these two sets would give you like a valid answer. So here's an example of like what this mechanism looks like. So we have some long sequence, and like let's say for example, like if your query is bi, like the closure of would be just like all of the symbols that are connected with b or I in the context. And so in this case, like it's a, b, I, and l, and we see like the model has like actually pretty good sense of what's going on here. So this plot is like the logits of the model at the b token when it's going to predict I, which is like what the goal of the model should be is like predict some token that is like connected to B. So it has a sense of like what are the elements that are connected to B. And then the same thing, if you like stick in a different query for the same sequence, it picks out all of the other elements that are attached to that one. So like for H, it knows that like C, E, F, H, N, and P are all in the same group. So that's what we call the closure, is sort of the model's ability to compute like which elements are associated with itself in the context. And then cancellation is kind of this idea of like, so like if something shares an element with the question, so like if your question is P times E, you can go back and look at like one of these queries, for example, so like A times E, so these share E and E, and so we can like eliminate F as an answer. And so if you do this for like all of the ones that share P or E in the context, you might get out that like the closure is P, E, F, A, and N, and like the set you can cancel out is like P, E, F, and N, and so what's left is just A, and so subtracting them gives you just like a single answer. Yeah. So any questions about how that might work, or what's going on here?
So if we don't have all the negative cases available in the training data, like for example, in this case, the model will have to go back and look at all the other examples where it can find the elements to cancel out. If it's not able to find all the elements, then it can get a wrong answer, right?
Right. So yeah, so this mechanism depends on like being able to like cancel them out. So let's say like you can only cancel out 3 of the 5, then like it would only be able to like narrow it down to 2, right? And you'd need something else to like to help you pick an answer. Yeah, that's right. And so like if you remember from, there was like a plot where we showed like like what kinds of like it's like the what do we call it? The coverage of these algorithms. So like this gets better with more context, right? Because there's more things to cancel.
Yeah. Makes sense.
Yeah. Okay. Let's see. Yeah. So here's just an example of what this looks like. So there's like just some evidence of like what this cancellation set might look like. So there's like 2 heads, for example, like in this the one model that we analyze here, where like this head at the equals token here is attending to stuff that shares H on the left. And like so it sees E and F as answers and like it demotes E and F. And then like this head 3.4 looks at stuff that shares C on the right. It also has some blend, like it also blends stuff that isn't C on the right, but like a lot of it is like C on the right. So like P, C equals H, and C equals C. It also has, some bleed over with like shares H just in general, and like weakly demotes those answers as well, but like C and F are the ones that are demoted the most. And so like combining sort of this with like its closure, you'd get something out where you might be able to find the right answer. Yeah, I think let me see. In the I must have hidden it. Sorry. I'll go find it later, but pretty soon we'll update the archive version. There's some other experiments we ran where we train subspaces to represent these closure and cancellation sets, and find that the only place you can really represent these is in like the final attention layer. So that's where they're getting computed, and that it like they're pretty cleanly separated from each other. So like computing which elements are in your group is different from computing which ones are getting canceled out. Yeah, I wonder if I can find the. Too many. Okay. This is, I didn't quite finish these slides yet, but so basically, I don't know, yeah, if people have questions, we can talk about it later. Yeah, so that's the closure-based cancellation mechanism that we found. I think it's pretty cool. And then the last thing that we look at is like the development of these algorithms over time. So yeah, we see a lot of, I noticed Bernie asked a question in the chat here. There's a lot of grokking, which I think is pretty cool. And it sort of follows my intuition for like the like complexity of the algorithms that get learned. So like the way that we do this is we have our little probing data sets of the different tasks or like sub algorithms that a model might learn. And we just like periodically evaluate them throughout the course of training of different model checkpoints. And so like, and then compare it to like the loss landscape. So on the top, we've got the training loss, and on the bottom, we've got like accuracy over different metrics that we compute. So like the first thing that the model learns, for example, is like just to compute like structural tokens, like the commas and the equals. And then it slowly learns kind of this like closure mechanism. So like just predicting which elements go together in the same group or not. And at the same time, it's getting about 50% accuracy on the identity task, which would come from just like predicting one of the answers in the question. Like basically, like if you just always predict one of the final two symbols, you'd get about 50%, right? And then there's this sort of drop when in identity accuracy when it learns that, oh, I can actually just like copy stuff from the context instead of just always predicting one of the final two symbols. And then it learns, like quickly learns how to copy, which also like coincides with learning this like commutative heuristic, which sort of gets refined later. And then I think what is maybe my favorite part is that this like 6 and 7 pattern here of when like the cancellation mechanism and the identity mechanism go up sort of corresponds to this time when the model is learning that it can cancel stuff. So you can kind of think of like like the closure-based cancellation and the identity are like made up of like two sub-mechanisms, both that have like a promotion part and that have a demotion part. And so the promotion part is sort of learned early, and then the demotion part is sort of learned later after it learns how to copy. And then like, yeah, those get refined over time. And then associativity gets learned later, though it's like never quite reaches 100%. And I know, and then yeah. So anyway, I thought these were pretty nice. Sort of matches my intuition for like copying seems easier than like these other mechanisms that we observed. But it was cool to see these like splits between like just promoting stuff that you've seen before in the context that's related versus like learning how to be more targeted in like promoting and demoting things that are relevant. So yeah, there's obviously more details in the paper, but yeah, thanks. I think that's it. And then if people have questions, we can chat. So
Yeah, thank you so much.
I wonder
Let's
if
see.
the associativity would eventually grow even more with longer training in the loss graph.
Yeah, so we did spend some time trying to figure out what's going on here. The original model that we analyzed, so this is actually averaged over like, I guess this one's over 4. So we trained like, I don't know, hundreds of models. And so these ones are actually quite a bit better than the original model that we analyzed. So like I think that one got around like 60% associativity score, and this one's at like 80%. So maybe these ones actually like learned it or partially learned something close to what associativity might do. But in all the ones that we trained, we never saw any that were able to get like 100% on associativity. Even with like slightly bigger models, though I didn't do extensive sweep. I did like a reasonably sized big sweep, but yeah, I don't know. It seems like this associativity is like a slightly harder problem, and it might just have to do with like being able to chain stuff together well. I don't know. Yeah, it'd be like that definitely is like an open question here that I'd be interested in figuring out what's going on there. And that's also the one mechanism that like because we were analyzing one of the earlier models we had trained that like was working well but was worse on associativity that we didn't quite get to understand that mechanism either very well. So yeah.
I wonder if bigger model and more data in the bit relevant sense would help.
It could be as simple as that. There might be like some fundamental difficulty with like the kinds of like maybe there's just like I don't know. It seems like it should be able to learn it, and it maybe is learning something close to that if it's getting like 60 to 80%. But we'll see. But yeah, I'm happy to if someone is interested in looking at it some more, happy to chat. Bigger model, more data, yeah. Could be the easy solution.
Have you tried like differently sized models, maybe some scaling laws or something?
Yeah, yes. Let me we could pull up let me see if I can reshare a different screen. Here. Okay, let me try and reshare. Change stream. If I do. Oh, let me just make this a new. Then I could pick this, I bet. No. Let me move this to a new screen. Yeah, there are some nice scaling laws. I'm trying to see. Okay, new desktop. That's what I want to move it to. Here.
Maybe you have to first disable the stream and then share a different screen or the whole whole monitor.
Okay, let me try that.
Right now you're sharing just the presentation screen probably, yeah?
Yeah.
Of the app. I think you instead of choosing like just one app, you can like share the entire screen.
The whole screen. Great, I can do that.
Yeah.
Okay. Okay, you're probably seeing Discord, but then okay, can you see this is just overleaf raw overleaf,
now we see Discord.
Oh, you see Discord. Dang it. Okay, let me try again.
Did you only entire screen on top?
Oh, there we go.
Yes, then share screen. And click on
Okay.
share. You didn't click. Oh yeah, now we can see overleaf.
I can see overleaf here. Okay.
Yes.
Yeah, so whoops. Okay. So like we did play around with like different hyperparameters for training. So like this is, for example, loss and evaluation accuracy for like number of layers. And so like 2 up to 10, and like for smaller models you have like a longer performance plateau, and like you don't quite get the same accuracy as you do with like bigger models. Same kind of thing here, like you need a big enough dimension to solve these for some reason. There's like some inherent capacity needed. Like 128 isn't enough and you just sort of just plateau, But for all the ones that we tried up to like 10 layers, and like it didn't seem like there was a very consistent pattern between like how good associativity is just based on layers. But maybe there's some sweet spot between like these were all getting like if you have a bigger hidden dimension, these were getting slightly better. That I guess that is the one trend that works. Like bigger hidden dimension meant better associativity. So maybe that's the key, is you just need a really wide network. I'm not exactly sure what kinds of like information is getting even stored there, but that would be one axis to scale, I guess, if you wanted to push associativity even more, maybe.
The layer variability is interesting, how it screws up with the associativity in such irregular way.
Yeah.
First it grows up, then down, then up again. All right.
Yeah, I don't know. I'm not
I
really
wonder
sure
if what also if how like seed matters.
Yeah, so we did play around with seed. So these are the plot with the phase transitions is over different seeds of the same model, and it seemed like it was pretty consistent. Like maybe many minor like variability, but seed's pretty consistent. Let's see. This is also seed, so like eval accuracy is maybe like slightly lower for some seeds than others. But not like too. I mean, I don't know. This is like 90 versus close to 100. So maybe the seed does matter quite a bit more too than I thought. We also played around with there's kind of this parameter for like the how often you sample a new group. So like how many groups you're mixing in the same context or not. So if you just like are using a single group in the context, that's this blue one, the like dark one. And if you're sampling the most number of groups that you can, like always filling up the number of variables that you have, that's this yellow one. So
that's a triangle for a single group, the purple one.
So it's not a single group. It's a single group in for a given sequence. Because remember, like we mix many groups in the same sequence. But this one is like if you were to just have one group in a sequence at a time. Yeah.
I see. Like the graph looks kind of grockish or phase changes.
Yeah, I mean, they all sort of are like that. And often like a lot of similar to the phase transitions we saw earlier, like a lot of that is related to this, like the right after it learns to copy, then like a lot of the other like mechanisms get learned. So
the identity is interesting, how it first goes up, then down, and then up.
Yeah. Okay. Anyway, yeah. I don't know if there's any other.
And how the purple one goes up much later than the other ones.
Yeah, the commutative. Let's see. Yeah, I think there's quite a few open questions here that I'd be interested in looking at. But
yeah, that's another thing you said you wrote in the chat, future directions and open questions.
Yeah. Cool. I'll make a little draft or something and post it here. I don't know if I guess like off the top of my head, the things that are like open, like associativity is still an open question, for example. I think it'd be interesting to study how that works in the setting. Also just from the algorithmic analysis, like there is something else that the model, like there's some other heuristics or something that the model learned that beyond like the 5 that we like probed for initially, like there's like the gray gap between what is like theoretically solvable just from the 5 algorithms versus like what the model learned empirically. So there's something else that the model learned. I'm not sure what's going on there. And then like have some other interesting thoughts about like it might be cool to play around with like mixing, for example, like maybe so like in natural language, when we think about like tokens as variables, like we use just like X and Y and letters, but then there's also like other words that do have fixed meaning. And so like it might be interesting to have like a mixed setting where like some tokens do have fixed meaning, but others can be variables, for example. And then trying to see like what gets learned there. There might be interesting parallels between like the original grokking setup where like all the numbers have fixed meaning, and you might be able to like interpolate between like, oh, does it learn the like clock algorithm versus like learning these like symbolic algorithms that we saw, like maybe there's some like interesting transition between like how often you cause a number to be a variable that like transitions it or something, I don't know. But yeah, if you're interested in playing around with it, feel free to DM and we can brainstorm some more. But those are just some off the top of my head, I guess. So anyway, yeah, thanks everybody.
One thing
Yeah.
in this Discord we are trying is like all sorts of toy models. So
Okay.
this is very, very relevant to, this is a special case of a toy model, you could say, or like
Cool. Yeah.
Foundational group model.
Yeah. So I when we initially started this project, the thing we thought that these models were going to learn was like it will just like learn the reverse mapping. Like you just like encode some group with some arbitrary variables, and like hopefully it will just like learn to decode the group, and then just like use one of the algorithms that we had already seen. But that's like, so we were looking for that for a while and never found it. But there might be like some way to induce that if you like in this like setting where some tokens are fixed and some are variable or something. But cool, yeah. I guess I hadn't seen what other toy model stuff people are working on, but I'd be curious to. Is there a specific channel for that?
Not sure if exactly. Part of what we're also trying is like taking existing like that we know a ground truth solution to of some toy model.
Oh,
So
yeah.
like, and yeah, Victor has a project, for instance, and like then that's not published yet, and then see if Claude Code can do it on its own, and also figure out the same solution like a human would.
I see.
So that's one thing we're trying right now, for instance, and it's also a group basically. Yeah.
Gotcha. Cool.
Yeah, there's been some like toy model papers, but like on the Ringo, but not that many lately. I'm also interested in that. But yeah, I don't know.
Yeah, I guess my thoughts about toy models is like if you have a particular phenomena you want to study, I think toy models are great. Like but I also think like and I think it's been cool that like a lot of the stuff that's been found in toy models seems to generalize somewhat to big models, Like I think it'd be cool to also like I'm not sure exactly here like what the parallels would be for big models, but like trying to understand like what transfers would be interesting.
Something I've done is I also haven't published yet. It's like I was looking into, there was a phenomenon from a paper when I talk about out-of-context learning. Well, I think in the end they ended calling it like in context meta learning or something. which is about generalization, like from one task or another. On the paper, they had like definitions where they have some random string of letters, and they get the model to say that the random string of letters was equal to some name, and then ask questions about that famous person or whatever with this random string of names. I got the correct answers without training on the questions with that name. And I've looked into that, but with like modular multiplication and like some thing where I get the model to output some number for some alias token that correspond to the numbers. But I feel like I know the thing that happens there seems like it's very kind of janky and probably doesn't generalize to what's happening on bigger models except on a very vague way, right? Where it's like, yeah, it turns out the models just, in some sense, reuse some of the model, and for some of the mechanics for the multiplications when they do to learn the definitions, but that's pretty vague, and the actual thing that's happening there on the actual model, I figured out it's more kind of depends on details of whether how each of the things is structured and things with the attention patterns and so on. So yeah, I do plan to look into bigger models and see if I find something that in the language models I find something that relates. But yeah, I wouldn't be surprised if it's just not related. But it's true that at the same time, the whole modular addition stuff and seems to have generalized. So the toy models you can learn things from toy models that generalize to bigger models. It's just not always.
Yeah, I think there's definitely some merit. Like, I don't know. This setting was a lot of fun for me to study, of like trying to come up with a way to disentangle like priors from embeddings versus like what can be learned in context, And I think like there's probably a lot more things that models can do in context that we like that it's hard to study in real language models just because it's like mixed in with a lot of parameter priors, So there's been some cool papers trying to do something like this, where they like study the same problem, like a math problem where they like replace all the numbers with like letters and then show that like, oh, like models can actually reason about things symbolically, instead of like just having to like do the like actual arithmetic of computing the number, So, but yeah, I think it's like it's a challenging. So, anyway,
It would be nice if we had a lot more, like if something like the things where we automate researching reverse engineering toy models with code or something worked, and we could have a lot of examples of even tiny toy models for different tasks that we know how they work, and maybe there we could learn some things that are more general. But I don't know.
Or mapping the whole space.
Mm-hmm.
I kind of want to try mapping the whole space of like here you have like in your context you have a transformer trained on some subsets of groups basically, and like there are so many different algebraic structures that can be used. There are also so many other different groups and different instances of them. So like there seems to be, and like if you train them like this, you can possibly learn different algorithms with different configurations of the architecture, possibly not just transformers and so on. So I'm very, very curious about like how could this whole space of like mathematical toy models, as in trained on math tasks, could they be mapped, and like maybe like some some periodic table of like algorithms that are learned could be very interesting or something like that.
Yeah, but it feels like you definitely need to find a way to automate it to do that, because otherwise it will be
Yeah. Just forking some template or something like that.
Yeah.
Or mutating some template, basically. Yeah. That gives me some ideas. Okay. I like category theory, and categories are technically algebraic structures, so you could maybe do some transformers trained on categories somehow.
Yeah. You can like. I feel like even though we use groups, I feel like the setup is like pretty general. Like you could just have tokens represent some element of whatever structure you want to study, and then like
Yeah.
you could use categories, you could use non-groups, whatever. And then
Okay, one thing I kind of want to try now is if it can. Okay, I'm not sure what exactly I would predict there. Like the there's like not sure how much you know category theory, but like it's like this ultra general language that in which you can encode literally everything in math. Well, not literally, but almost everything. So like group theory, so like groups are just a special case of a category, which is a case for any math subfield. So I wonder if you could do some categorical algebra with just groups, and if it would learn similar algorithms or something like that. Since it's equivalent to the set theory representation of groups that everyone is using. I don't know. That could be interesting. But I'm not sure how you would encode commuting diagrams. Well, I guess you can do that. Agda does it. This is such a rabbit hole. Oh my god.
yeah, I mean, I think the other thing that was nice about groups is like there was already some nice like SymPy. I mean, SymPy has like just nice code for like simulating groups, So, but I'm not sure what other kinds of maybe there already are like support for other kinds of structures, but like we had to write up our own like quasi group implementation because it didn't seem like there was a great one.
What exactly does quasi group drop?
I think you drop inverses.
Mainly that associative and identity element properties are optional. Okay. Interesting.
I don't remember.
A quasi group as an identity element is often called a loop. There should be some better naming instead of all these random words. Oh my god.
Yeah. Okay, let me see. So, just respond.
Okay, if you. Okay, this is a good.
A quick logistics question: if I need to share the slides with somebody else, do you have them like online somewhere? I'm sure that you might want to keep working on them, and I don't need the most latest version. It's just like if I talk to somebody else about like what I learned in the talk, I need to reference a specific slide. It'd be easier to just, maybe there'll be a link included in the description in the YouTube recording. But if you can just like share it directly, that would be helpful. I didn't see a link within the first few slides itself.
Yeah, I can send you the slides.
Also, the website.
Cool. There's ODM. Yeah, that works.
Cool. Yeah.
Okay.
There is a website, but if there's a specific slide you're looking for, happy to send it as well. Yeah.
Yeah, I don't have a specific slide in mind. It's just like if it comes up in the future.
Sure. Yeah, I can send them.
Yeah, the website basically has the slides, but not the introduction of the first papers that lead up to this, basically. So it starts basically with the paper without the introduction in terms of slides, which makes sense. Yeah, toy models are very like I feel like there's so much mathematical structure in natural language as well, which
Yeah.
can be possibly mechanistically found. So I think toy models like this are like here's the structure directly, and whatever is like whatever insanity is learned in the all general natural language. Like since if you like train on both math and natural language, you also get like the Fourier loops and circles and stuff like this, like in the line breaking task paper. You still get it inside the general LM, so it somehow encodes in both the math stuff and also the language stuff, and reuses some language stuff possible. Like what the hell is happening there? I wonder how it structures it all, and how it also fails to structures it all.
I think the Questworld paper, I think with the counting task one, does have I think are good arguments for why you should expect to see the same kind of representation for like all kind of things that are some one-dimensional thing that you want to represent without a lot of overlaps.
Oh yeah. Also, the dates, for example, are on a circle, or yeah, some other. Yeah, we have kind of an inside joke here at this point about circles. Circles are everywhere in Mech Interp, literally.
Yeah, if I get into AI psychosis, it's probably going to be circle related. Okay, yeah.
Lines and loops.
We were hoping to find circles in this paper, and then like as we were doing the research, but just like didn't end up happening. And I guess my takeaway was like when you're just like working with things that are like just symbols, like there's no reason to really encode any information, and you can just like reason about it purely in context, you know. Because when we were doing like PCA on the embeddings, we were like, oh, like hopefully we'll just like find some nice like circles, and then but never found anything like that.
No Fourier stuff.
No, yeah, unfortunately. But I think it makes sense though, right? Like there's no way to distinguish between any of the symbols beforehand, because like A in one context could be the identity, and in another context it can just be like some random rotation or like flip or something. And so like there's no reason to,
the modular addition transformer learns this trigonometric algorithm.
In the token embeddings, right?
That's basically just cyclic group, but then so here you have multiple groups, cyclic and the other ones, and it doesn't learn something trigonometric. I wonder like when it learns the trigonometric, when it doesn't.
He's saying so the thing is in that one the embeddings mean something, right? So you should expect to see some structure on the embeddings, because the embeddings is just one number. Here the embeddings change the meaning depending on the context, if I understand correctly, right?
Yeah, so I think our paper is sort of like 2 steps away, right? So like we have multiple groups, some that aren't cyclic, and the other thing is like the variable embeddings. So, but it might be interesting. There's maybe like some natural interpolation between like the original grokking setup with like modular arithmetic and like what we study here. Like maybe there's some like tipping point between like when the cyclic structure gets learned versus when like the symbolic structure gets learned, you know. That might be interesting to study.
Or maybe it could learn both somehow in some weird.
Yeah, and maybe there's like some competition between them. Yeah.
That sounds like state space worth exploring, I think.
That does always make me wonder, like, what happens if you fix the embeddings to not have any structure, to be like just some you know, I don't know, some thing where you have a different embedding for each one, but this there just doesn't have any special structure, and you train the model that way. If it learns something different, if it works better or something. Because right now, if your embeddings basically don't mean anything, just that they are different symbols. I will expect any structure of them on the embeddings is kind of going to be misleading the model.
Also, there's the positional embedding here. I wonder what would change if you didn't put in a positional embedding. Or put it in a different place of the model.
With
make it
linear
learnable.
models, they can just do things with attention to make their own positional embeddings.
Yeah.
Yeah, on small models, I might just break.
Probably.
Okay. Let's see.
Yeah, training a monster group would probably be impossible. In practice, since that's so gigantic. But you just need some support from NVIDIA. Yeah, like I wonder,
Are you planning
like, if you
train a
go
monster
ahead,
group?
say it
Do you
again.
want to talk to somebody? Do you want to train a monster group? Do you want to talk to somebody at NVIDIA?
Say again.
Do you want to talk to somebody at NVIDIA about training a monster group? Do you have like a proposal?
Yeah, I'm just joking that like you would need a lot of compute, I think, to make a similar setup for monster group, since monster group has like 200,000 elements, I think, something like that. So to show it to yeah, I think
mean,
at least.
That sounds like one thing where people that's nothing for the people training big language models anyway. But yeah.
Yeah.
Yeah, I'm not sure. Like based on what I'm understanding for you, just kind of whether they'd be interested. But yeah.
Also, Also, this architecture that you're using here has more layers. Oh, you did sweep the layer number in the paper.
Maybe it is possible. I think you may be underestimating how much you can do with a GPU on a tiny model.
Yeah. Yeah, number of layers. Interesting. How it changes. This sweeping of different number of layers, etc., of heads and so on. That's a thing I was also thinking about. Did someone do that for the modular edition task only? That could be done. I wanna do that. Okay. Yeah.
All right. I gotta head out, but appreciate the thoughts, and feel free to DM if you have more thoughts or want to follow up. But
yeah, thanks a lot. I'm glad to see more of these. Or maybe also if you want do you know the universality paper?
Yes. Yeah. I don't know why it didn't get cited. I thought it did somewhere, but I guess it got. I was just looking through my overleaf. Somehow got commented out.
Luckily, Neil isn't Schmidt-Huber, so you're safe.
Yeah, thanks for coming. And I also told Jannik, but if you at some point have other paper and want to come here, feel free to tell me. And I usually we have weeks where we don't have any paper and end up picking whatever I find on Twitter. So it's better if we have the authors for some paper.
Cool. Sounds good. Thanks, Victor.
Yeah.
All right.
Goodbye.